Hi, students. This lecture, we are going to talk about how to simulate silicon solar cell using CrossLight AppSips commercial software. I'm Icha Tsai, and let's get started. So in this project, we are going to use the layer project to define the device structure. We need to use the solution file to define our solver and detailed information. And we are going to use PLT files to plot the output data. Okay, this is very similar to LED simulations, but a little bit different is that I will upload um, solar silicon oxide, dioxide, and the solar N1.5. These two are spectrum information because we are simulating solar cell. So we need to define what is our spectrum that we want to simulate. So air mass 1.5 means that it's a spectrum profile that we measure on Earth, yeah, at the sea level. Yeah, if we want to simulate for extraterrestrial those applications, you should use like solar AM0. Yeah, that means you are using the spectrum profile at the outer space. Yeah, and if you want to simulate like a spectrum profile on Mars or Jupiter, then you need to search for their corresponding solar spectrum. Yeah. Okay, and these two files are attached with with this presentation slides. So here you need to like copy these two files into your project folder. Yes. And this is the device structure we are going to simulate today. So it's, you can see it's just like a simple NP minus P plus structure. So we have first the layer of 500 nanometer of N silicon with a doping concentration of 2 times 10 to the 19. We have a like a slightly p-doped 4 micrometer thick layer in the middle, and on top of it is 500 nanometer P plus layer. And we defined N contact to be like 6 micrometer, and the P contact, I believe it should be around 500 nanometer. Yes, 500 nanometer. So here it would be like 500 nanometer, and 5 micron in this middle column. Yes. Okay, so in the very beginning, we are going to define our column information. We are going to have 3 columns. In the column 1, our column width is 0.5 micrometer, which implies 500 nanometer. And in the second column, we have 5 micrometer width. And in the third column, we are going to have 500 nanometer width. Yeah, and we define our bottom contact to be ohmic for and we have 3 bottom contacts because for individual column number, we're going to define it individually. So in the column 1, we define the bottom contact from here to here. And then in this line of code, we define the bottom contact from here to here. Okay, and similar for the third syntax here. The bottom contact at the bottom here defines the contact region from here to here. Okay. Okay. So this is the first layer we are going to define is N plus silicon with a doping concentration of 2 times 10 to the 19. And the layer thickness is 500 nanometer. Yeah. And you define the layer material for the column 1, column 2, column 3, and you define each layer thickness with the mesh information. And then you define the N doping concentration for column 1, column 2, column 3. Yes. And here we use a non-uniform mesh R ratio of 0.8. What does that mean is that the mesh is increasingly dense toward when Y increase. Y is the layer direction. Okay, then we define the lightly doped P region, which has a 4 micrometer thickness. The doping concentration is 2 times 10 to the 11, but here I use 2 times 10 to the 18 because the default unit is per meter square, per meter cube. So you need to make a conversion from centimeter cube to meter cube. Okay, and on top of it is P plus layer. So here we use a R ratio of minus 1.2. What does that mean is your mesh is becoming loosened as you increase your Y value. Okay, so we are going to have dense mesh in this interface and this interface, and also a lot of mesh would generate in this lightly doped P region. Okay, and then eventually we are going to add top contact in the first column and the third column. Yeah, this top contact is for P contact. Okay, then we generate the geometry file and generate mesh. So this is the mesh information you can see. Yep. And next step, we are going to define the solution file. So similar to LED simulations, we are going to load the mesh information. We need to include the material information. We include the doping information. Those are automatically generated once you have your .layer file. And then we define the file name of your output file. Okay, and similarly, we are going to give some default information to our Newton solver. Yeah, so we use like a damping step of 5. You can use the default value. I'm going to talk about if your simulation does not converge, what kind of parameter you are going to play with to make it to solve the convergence issue. But here you can use the default value. And then we solve for equilibrium conditions, which means that we don't apply any bias. The reason behind it is because we want to solve the Poisson equation first. And then once we reach the good convergence, then we start to iterate by increasing the bias conditions. And then so that we can have a good starting point, good initial guess. And then we define a Newton solver for it. You can use the same Newton parameters before this equilibrium conditions. I guess it still can reach a good convergence. So, but this is just for your information. Here we define 2 separate Newton solver, but to my own opinion, I guess if you define, if you use the Newton solver shown in the bottom line here for equilibrium conditions, I think it can still reach a good convergence. Okay, so one thing different from LED simulation is that we are going to include light into our system. So in order to use the spectrum file, we need to use a scan command for the light variable range from 0 to 1. That corresponds to turn the light on and off. So here we turn on the light from 0 and value to 1, meaning that we are turning on the light. We ramp up the light. That is what this code for. And then we applied a forward bias to offset the photocurrent. So we apply the forward bias from 0 to minus 0.75. The reason we choose this value is because the open circuit voltage is roughly below like 0.8 or 0.9 for silicon solar cell. So yeah, we ramp up our voltage step from 0 to minus 0.75. Yeah. And then in this code, light power spectrum file solar and 1.5. So we define our spectrum profile. As I mentioned earlier, we provide the AN 1.5 solar spectrum, and the light direction, instant direction is from top. So yeah. And then we define optics coating. So this optic coating defines the optical property of the external boundary. So here we assume that this solar cell is bounded by, is encapsulated in the silicon oxide. Yes, and you can have, you can include the optical coating and specify the spectrum profile of silicon oxide. And we assume that silicon oxide has a thickness of 0.1 micron. Yeah, so we include this into our system. And then we enable back reflection. What does that mean? Is that so when solar cell is exposed under sunlight, the sun will hit to the bottom contact, and if we enable back reflection, that means the sunlight is going to reflect back to the solar cell. It's not going to penetrate through the solar cell. So if you enable this, then your optic power and efficiency is going to go up. Yes, but it also depends on what is your assumption for the bottom contact. So here we assume that your bottom contact is like a Bragg refractor with 100% reflection efficiency. Okay. So in solar cell, we don't have any quantum well structure, so you can see that it's relatively simple compared to LED simulation. But here, the only difference is that you need to include like light power, you need to include the spectrum profile, and you need to include the scan of the light instant from top of the solar cell. Okay, so once you complete the simulation, and you need to plot your data. So here, we are going to plot the band diagram under equilibrium condition. This is what this flux does, and so when we turn on the light and we want to see how does the band diagram changes compared to under the equilibrium condition. Yeah, so this is what this flux does. Okay. In the third figure, we are going to plot the instant power, and then we scan the data from the second bias point to the third bias point, and you can find its corresponding bias condition, its voltage, and the corresponding current under the same folder. And in this plot scan, you are going to get the IV curve. Yeah, you're going to get the IV curve of your data. So please make sure that you put like a scale vertical -10 and the scale horizontal -1. The reason behind it is because in solar cell simulation, your voltage and the current directions are actually opposite. So for example, in your voltage sweep, you put like a minus voltage, right? And then you in the current sweep, in the your current direction is actually flipped to a negative sign. So if you want to plot it like in a positive sign, then you need to multiply your voltage by -1 and your current by -10. And the reason why it's -10 is because you want to make a unit conversion. The default unit for current density is amp per meter. But if you want to convert it to a milliamp per centimeter, you need to multiply this number by 10. So that's the reason why you end up with like multiplying -10 in here. Okay. So this is something you need to keep in mind. Yes. And here we are introducing new command, parameter extract. So this will extract the value from the 1D plot based on the numerical formulas, including like minimum, maximum, and the maximum product XY. The reason we are doing that is because we want to extract open circuit voltage or short circuit current or the maximum power generated by this solar cell. Because we want to get the maximum power to calculate its maximum efficiency, conversion efficiency. So the first plot, we are going to extract the open circuit voltage. So you can see parameter extraction, append data equals to yes, and we want to output this open circuit voltage in this separate file called voc.txt. This is horizontal intercept equal to 0. What does that mean is that in the following plot, this plot scan, in this plot scan, it will show the voltage as a function of current, and we want to extract the parameter where the voltage, where the current is 0, because that is how we define open circuit voltage. So this plot scan is to show the voltage as a function of current, and scale vertical. So you multiply this current density by 1.66667 times 10 to the 5. And the reason we are scaling this current density by this amount of number is because the default unit of current density is amp per meter. But if you want to plot it in the unit of amp per meter square, we need to divide this number, this amp per meter, by the contact width. Because we have 6 micrometer contact width, so we need to divide this number by 6 micrometer, which is equivalent to multiplying 1.666 times the 10 to the 5. Yeah. And scale horizontal -1, this means that we want to flip the sign of the voltage. So originally this voltage is minus, it's negative. So once we multiply the negative voltage with this -1, it becomes positive voltage. Yeah, because this is for visualization. We want to see positive voltage and the positive current. Okay. Yes. And then we want to find the short circuit current density. Similarly, we use parameter extract, append data, yes. We want to store this short circuit current to this jsc.txt. And we want to fit the voltage from 0.02 to 0.2 so that we cover this short circuit range. Okay. Yeah. And then similarly, we just copy paste this IV curve to here. So they are similar. They are the same. They are actually the same. Yeah. And then we want to extract the product of the voltage and the current density. We want to find the maximum value. So we use parameter extract, append data equals to yes. We store the product. We can call it like the maximum optical power, the maximum electric power under this in this file. So you can set that XY horizontal from 0 to XY product search, XY vertical from 0. So we are scanning the XY, the product of XY in the horizontal direction and the XY in the vertical direction. So we are scanning if like all combinations of voltage and the current density. Yeah. So for your final project, you would just need to copy paste two lines of code. Then you can search the maximum product of your solar cell between like voltage and the current density. So, okay, and yeah, so if you define your parameter extraction, you need to put plot scan so that this parameter extraction works for this plot. Yeah, and this plot is the same as the previous one. Okay, and then we want to find the maximum efficiency of the solar cell. So we use parameter extract command to find the maximum product from solar cell IV curve and convert the IV curve product to efficiency by dividing this optical power with this solar optical power intensity of 963 watts per meter square. Yep. If you perform the integration of this spectrum profile, you will find out that the incident optical power is equal to this value. Yes, and if you divide it by this value, which is equivalent to multiplying on 1.03782 times 10 to the minus 3. So we are going to use this code, the code that we are going to find the maximum product here, but with one small modification. We are going to multiply this maximum product by this number, 1.03 10 times 10 to the minus 3. And this will give us the efficiency. So this efficiency is going to store under EFF.txt file. And then we plot the IV curve again. Yeah, so that is the end of the POT file. And once you run the simulation, so this will show the band diagram under equilibrium condition. This will show the band diagram under light inject when we turn on the lights. And this is like a power density in the solar cell. And this is the IV curve. You can see on the left-hand side, ampemeter, milliamp per meter square as a function of contact voltage. And now you can see it's positive, although we set like minus 0.75 previously. So you can see this current density below 0. And these regions, these minus current density regions are where where this solar cell operates. And yeah, if you just extract this region and plot it, and by flipping the sign of the current density, you will get this. And you can see that your open circuit voltage is about 0.68 roughly volt, 0.68 volts. Your short circuit current is about like 170 amp per meter square. Okay, so this is exactly what you will get using the parameter extract syntax. So you can see your open circuit voltage is about 0.68, short circuit current 170, around 170 amp per meter square. Your maximum power extracted from the IV curve is 96 roughly watts per meter square. Your conversion efficiency is about 10%. So this is roughly the conversion efficiency for like a typical silicon solar cell without any optimization. So yeah. So if you have any problems with understanding how a command or keyword functions, you can go to wizards and or you can look up the manual to see what does those parameters mean. Yeah. So these are additional comments. If you have like a convergence issue, you need to work with Newton method. If your layer file is properly defined and without any issue, most of the time it's because of uh, this Newton method. So when solution is not converging, some safe things you can try is to reduce damping steps from 1 to 0.5 or even smaller. Or you can try larger maximum iteration number because you can control the maximum number of iterations. Sometimes it just the arrow just does not reduce that fast. So you reach to the maximum iteration number. Typically, we set it like 100 because most of the iteration will finish within like 10 iterations or 20 iterations. There are other things you can try. You can increase the optimal iteration number, but those are just based on what kind of device structure you are simulating. Sometimes it's just your structure is too complicated to reach a good convergence. Yeah. For light power spectrum profile, so the strong spectrum profile like solar.an15 or solar.silicon dioxide, in that spectrum file, you are going to provide the wavelength as a function of spectral density. And you need to know that what is the default unit for the wavelength and what's the default unit for the spectral density. And if you integrate the spectral density over a wavelength, you will get the solar power density, which is defined in units of watts per meter square. Now, typically, 1,000 watts per meter squared is for air mass 1.5, but the actual integrations will give you like 963.56 watts per meter square. Yeah, but you need to keep in mind that you need to use the actual one, yeah, for your higher accuracy. And you need to define the optic coating spectrum file. We use this in solar dot silicon dioxide file. You need to define your own. If you want to use different coating, yeah, other than silicon dioxide, then you need to provide your own profile for wavelength, reflective index, and the extinction coefficient. Extinction coefficient. Yeah. Yeah. The reason we are multiplying our horizontal scale to -1 is because we want to flip the x-axis sign. Typically, our x-axis is voltage, so we want to have positive voltage. And in 2D simulation, the current density is output in units of amp per meter. If we want to convert it to like amp per meter square, this is the typical definition of current density. Then we need to divide this number by the width of the contact. So here we consider like 6 micrometer contact width. So we need to divide this number by 6 micrometer, which is equivalent to multiplying 1.6666 times 10 to the 5. Yeah. And the efficiency of the solar cell is the product of open circuit voltage, short circuit current, and the fill factor, and divided by the instant optical power density. And this one, yeah, so the reciprocal of instant optical power density is 1.0378 times to the 10 to the minus 3. Yep. Yes. Yep. And you can use cross-slide view to plot the band diagram, as I mentioned in LED simulations. But you can also you can output the file in CSV using this command. Yeah. Yeah. Um, I think those are just small tips for you to output the Venn diagram. Um, so if you are using your own material parameters, you need to check the macro under CrossLight folder. Yeah, I will teach how to modify the macro in a bonus content, but here you just need to know that these parameters are changeable. You can define your own material. You can change the parameters based on the material you choose. Yeah, here I just take one example, like a band gap. The band gap defined in CrossLight, it depends on the temperature conditions. So the band gap, as you know, it is going to be changed depending on the temperature conditions and following Varshini's empirical equation. Varshini empirical equations is defined like this. The band gap at temperature T is equal to the band gap at when under 0K minus alpha T squared divided by beta plus T. And this alpha and the beta are Varshini parameters. These are empirical parameters. Yep. Yeah, and if you perform your simulation at like a 500K, you can see that your bulk band gap is 1.06 in CrossLight. And if you do the like a hand calculation, you will find out that this matches with the Varshini equation. Yep. And that is for Sourcel. If you have any questions, I would suggest you to come to office hour and we can talk in depth about if you have any questions about your question. Yeah. Yeah, thank you very much. Have a good day.